Hi, everyone. Welcome to our seminar tonight or today for those of you who are in Korea or other parts of the world. My name is Somaya Sadat. I'm the Assistant Director at the Center for Analytics and AI Engineering at the University of Toronto. It's my absolute pleasure to welcome you to today's seminar by Professor Nicolas Papernot. As you may know, this is a joint seminar series that we are running with the University of Seoul in Korea, and it would run for another 6 weeks. So I invite you all to check the events on our website and sign up for the rest of the seminars. Today's seminar, the topic is the role of randomization in trustworthy machine learning. Before just diving into the seminar, I'll give you a quick introduction to Nicolas, and then I'll pass it to Nicolas. So Nicolas Papernot is an assistant professor of computer engineering and computer science at the University of Toronto. He also holds the Canada CFAR AI chair at the Vector Institute and a faculty affiliate at the Schwartz-Reisman Institute. His research interests span the security and privacy of machine learning. Some of his group's recent projects include proof of learning, collaborative learning beyond federation, dataset inference, and machine learning. Nicolas is an Alfred P. Sloan Research Fellow in Computer Science. His work on differentially private machine learning was awarded an outstanding paper at ICLR 2022 and a best paper at ICLR 2017. He serves as an associate chair of the IEEE Symposium on Security and Privacy and an area chair of NORIPS. He co-created and will co-chair the first IEEE conference on secure and trustworthy machine learning in 2023. Nicolas earned his PhD at the Pennsylvania State University, working with Professor Patrick McDaniel and supported by a Google PhD fellowship. Upon graduating, he spent a year at Google Brain, where he still spends some of his time. With that introduction, I'd like to pass it to Nicolas for the seminar.
Thank you so much, Somaya, for the introduction. I'm very excited to be here tonight and this morning, I guess, in Seoul. So today I wanted to basically give a talk that covers both security and privacy research in machine learning. And the unifying theme for these two different sort of agendas is essentially the role that randomization plays in making models that are both more secure and also more private to defend against attacks that we might carry in either of these settings. So I'll start with the first part of the talk will be about security, about in particular robustness to adversarial examples. And then later on, I'll signal when I transition to the part on privacy, and you'll see that there are some interesting connections to be drawn. Before I get started, I want to highlight that this is work that I've done in collaboration with many others, including students. So I try to credit them on the slides, and I really encourage you to take a look at their websites to learn more about other papers that they have participated in. So here, the first problem we're thinking about is how do we defend against adversarial examples? If you're not familiar with this phenomenon, the idea is that we can take images like this image here of a panda that is originally correctly classified by a machine learning model, and then introduce a perturbation to this image that will force the model to misclassify it. So for instance, this image has actually been perturbed using an adversarial example algorithm, and it's now classified as given by the machine learning model. Okay, and so recently one avenue that people have been exploring to essentially defend against adversarial examples is to look at many randomly perturbed version of the input that we are asked to classify, and to sort of get a collective vote on these perturbed variant of the image to get a sense of what would be really the label that we should be predicting. So for instance, you could imagine applying a lot of random rotations to the image, and then to pass those into the classifier, and maybe you'll be able to tell now that this is a panda correctly. And so the question that I'm going to ask in this first part of the talk is whether this idea of introducing a random pre-processing defense before the machine learning model is applied does provide security, in the sense that it makes it harder for an adversary to find an adversarial example that will evade such a defended model. And the intuition here is pretty simple, is that if the adversary does not know what angle I'm going to rotate the image at, then they have to sort of find an adversarial example that will be robust to all of these possible rotations that I might apply as a defender. Okay, and so if we look at the field that has looked at these pre-processing defenses, well, we see that sort of the attack and defense arms race that we've typically observed in adversarial examples here is again occurring, where we have initial ideas like what I was describing, where random cropping, random rescaling, that was then later evaded. Then we had another round of such defenses, such as mix-up, random pixel dropping, that again lead to new forms of adaptive attacks, and so on. And so, but this is continuing to this point where recently, so we wrote this project last year, and so last year there was, for instance, a proposal of using diffusion models as a way to remove perturbations from adversarial images before they are passed onto the classifier. Okay, and so what we've learned from this interaction between attackers and defenders is that it's really hard to evaluate these adaptive attacks, to also design them. The reason is that the reason that it's hard to evaluate is that often these randomized defenses, these stochastic preprocessing defenses, they actually introduce a pretty significant cost to researchers that want to evaluate the performance of models that deploy these defenses. So, for instance, the last proposal here that I was mentioning, you know, it will take 1 to 4 high-end GPUs with a lot of memory before you're able to evaluate this defense. And so this means it's just harder for researchers to investigate whether or not the claims of robustness that are made really sustain more scrutiny. And the same thing here with this previous defense that was basically found to be broken only 3 years only 3 years after being published. And so the takeaway from these lessons that we have learned, and what remains to be understood, is really that we don't have a good sense of whether or not randomness provides this robustness as we expect. And we also don't know how to avoid some of the pitfalls that existing stochastic preprocessing defenses have faced as we design new defenses. Okay, and so the point of this first part of the talk is to really deep dive on these pre-processing defenses and try to understand what are their fundamental limitations. All right, so the first part is to show that there is really not as much randomness in these stochastic preprocessing defenses than people might think. And so this is something that we've actually observed when we look at something like expectations over transformation, which is an attack where essentially the adversary tries to find an adversarial example that will sustain, essentially, the perturbation will be sustained as we apply a series of transformations to the image. And so that's where the name expectation over transformation comes from. And this is something that we've seen in the literature, that using attacks that deploy EOT, expectations over transformation, is becoming a standard way to evaluate pre-processing defenses. And so we actually see in work from last year that this is sort of now a prerequisite to publish papers on these kinds of defenses, that we expect to see some form of evaluation using an attack that provides expectations over transformations. And we actually showed in the first sort of set of evaluation results that this is really not clear how much security we're getting from knowing that we can defend against these expectation over transformation attacks. And in particular, the fact that we're evaluating on these attacks doesn't really give us a good sense of how much randomness is actually being introduced by the stochastic defenses. And so what we look at in this particular table here is we have here these 5 defenses. And originally, following best practices in the community, these defenses were evaluated using adaptive attacks that deploy these expectations over transformation. And we can see that they are very effective in the sense that they are defending 100% of the time. So basically, these attacks are effective. Okay. And we can see here that the number of samples that are being used by the expectation over transformation is significant. In this case, we have to use 1,000. And we're using, again, here, this is the number of iterations in the attack, okay? So what we're doing here is saying, well, now that we know that these here, this is a success rate of the adversary, and what this is showing here is, okay, the success rate of the adversary deploying EOT is 100%. But does that mean that EOT is necessary? Well, what we found in this second set of experiments is that's not the case, actually. So here what we're doing is now we're disabling expectations over transformations. You can see that M is set to 1 here across the different rows. And instead, what we've done is introduce more iterations for the adversary. So imagine we're using something like projected gradient descent. Now we're introducing more steps as we're computing the perturbations. And we find that actually the success rate is, again, fairly large, very close to 100%, despite the fact that we haven't done any form of expectations over transformation in our attack. And so what this shows is that really the standard attacks that we were using before we came up with these stochastic preprocessing defenses actually are also able to evade these stochastic preprocessing defenses. All we needed to do is to adapt the number of iterations, the number of steps, and the learning rate. Okay. And so what that means is that these defenses don't introduce as much randomness as we expected. And we can see this here, where when we have here, we're varying the randomness that is being introduced. So here we have low randomness, here we have high randomness. What we can see is in the low randomness setting, we are already able to evade the model quite often, even if we don't use EOT, as long as we have enough PGD steps. And if we move up these different rows, we actually don't get much more success rate. Now, if we look at this setting where we do have high randomness, then we can see that basically using EOT improves the results beyond what can be done by improving the number of queries here. When we compare the number of queries here between these 2 circles and these 2 circles, we can see that by having more expectations over transformation, we are able to improve the success of the attack. And so this shows that once we have enough randomness, then yes, it does make sense to integrate expectations over transformation. It's just that the randomization's contribution to the robustness that we observed had been overestimated in prior work. Okay, and so to summarize what we've learned so far is, well, why can we break stochastic preprocessing defenses? Before, we thought this is because we have access to attacks that apply expectation or transformation. But now what we've learned is actually the reason we could evade these defenses is they were not as stochastic as we thought. Okay, and so now we're left with a second question, which is, what do I do, right? If I want to apply randomized defense, well, what we're going to try and understand is, can we get to a point where we have sufficient randomness that the defense is actually providing some robustness? Okay, and so this is what we're going to study now. And so the idea is to say, well, here, if we are going to introduce randomness, then we have this issue eventually that the more randomness we introduce, of course, the more the quality of the classifier will degrade because we're perturbing these inputs. We're eventually shifting the input distribution. And so here, what we are going to have to do as we increase the amount of randomness we inject as a defense is to basically train the model to be invariant to some of these transformations that we apply. And so what we're seeing here is we have a randomization space, and we're asking the defended model, which is basically applying this randomization, to make the same prediction than the original model. Okay, and so what we observe now is that if we are indeed going to have this model invariance, which is necessary to retain the accuracy of the model, then attacking the defended model is actually as simple as attacking the original model. And you can see this here, that it's basically reducing to an attack on the original model. And this is why we shouldn't expect stochastic preprocessing defenses to work. Okay, and so to give a bit more intuition, let me just take this very toy example. Imagine you have two Gaussians, and so here you have one class, here you have the second class in orange. And what we're interested in is essentially the ratio between the dotted area here and the shadowed area, okay? And that tells us how robust our classifier is. We can see here we're not robust in the middle because we can push a point by applying a small perturbation in the sense that it's smaller than a certain epsilon threshold that we define using here the L infinity norm. Then we can take the sample on the other side of the boundary. Okay, so what do we do when we apply stochastic preprocessing defenses? Well, we essentially shift one of the two Gaussians a little bit away from the boundary. And what that means here is that we have less vulnerable data points that in the region that I was just pointing out. And so this is why we are observing a certain form of robustness, okay? And that's why it appears in the first place that these stochastic preprocessing defenses work. But then if we look here on the right, once we train the model to be invariant to these transformations, to this randomization we apply, then essentially we're bringing back this Gaussian towards the decision boundary. And so we're back to what we had initially in the undefended model, more or less. And in fact, if we look in the limit, as we continue getting this sort of invariance, we eventually recover exactly the same situation. And so this is really what's interesting here, is that when the defended classifier achieves higher invariance to preserve utility, the robustness that we had observed strictly decreases. And it's actually some sort of a vicious circle where, because we have low robustness, we increase the amount of randomness that our preprocessing is deploying. And so this essentially means that the model becomes variant to this randomness, which explains why it performs poorly. And so to fix this, we are going to fine-tune on some of these preprocessed inputs during training, which now teaches the model to be invariant to randomness, but as a consequence, as we've just shown, decreases the robustness. And so we're left in this infinite loop where we actually are not able to explicitly control invariance, and we're actually not able to get significant robustness from applying these preprocessing defenses. And this is something that we can see in practice if you look at defenses that are using, for instance, a variant of randomized smoothing. If we don't fine-tune the model, what happens here is that we can see in the dotted line that the benign accuracy goes down quite significantly as we increase the amount of noise. And this noise is actually needed to be able to make the model more robust to the attack, because you can see in red, the dotted line is going down the attack success rate, okay? And so if we now fine-tune the model so that we recover some of this utility, so here you can see the green line, the solid line, now has very high accuracy, so that's good because we fine-tuned the model. Well, actually, you can see that most of the gains that we had observed in terms of decreasing the success rate of the attack have actually been reverted. And so we have this trade-off between robustness and utility. If we try to recover the utility, we lose the gains in robustness. And this is the same, it's even more extreme in the case of the targeted attack, where you can see here from the dotted line to the solid line in green, we do recover the utility by fine-tuning. But then if we look at the success rate here, before we fine-tune with the dotted line, the success rate is very low. We have a lot of robustness. But then as we fine-tune the model, the gains in robustness are cut in half. And so this is a good example. So what does this mean if we take a step back to finish this first part of the talk? Well, stochastic preprocessing defenses don't really provide robustness inherently. And really the only practical approach that we've seen so far is adversarial training that provides a significant improvement in the model's robustness. And instead, what the stochastic preprocessing defenses are doing is essentially shifting the input distributions. And so it introduces this trade-off between invariance and having the ability to defend. And so what does this mean for sort of researchers working in this space? Do we need to abandon these defenses? Well, not necessarily all the time. What we need to understand is better ways to introduce randomness in the machine learning pipeline to basically not have this trade-off between robustness and utility. And so we have to decouple effectively robustness and invariance, which is required for utility. And one way that we have been successful in doing this, in particular in the audio domain, is to look for non-transferable subproblems that we can randomly basically go through to make predictions. And so this will allow us to not only increase the amount of randomness, but do so in a way that makes it harder for the adversary to evade all of these randomly perturbed inputs simultaneously, while at the same time retaining the utility, because these subproblems carry the same amount of information about whether the input is in a particular class or not. Okay, and so this concludes the first part of the talk. I'm going to pause here in case people have questions for just a few seconds, but otherwise I'll show you now in the second part of the talk how in the question of privacy for machine learning, we have instead made a lot of progress in how to understand what we should do with randomization in order to provide privacy. And so I hope this contrast between the two parts of the talk will give you good insights.
So please feel free to type any questions you have in the Q&A box during the questions.
So I don't see any questions in the Q&A, so maybe I'll continue with the second part.
Sure.
Yeah, so essentially what we've seen here is that we don't have a good idea of how to use randomization to improve robustness. In machine learning, at least, we haven't had a way that is practical for images. We've seen some progress in audio. What I'm going to do now is show you how randomization is being used to protect privacy in machine learning, and then we can contrast these to conclude the talk. So what do I mean by privacy? Well, essentially, privacy is a very subjective notion, but fortunately, computer scientists have agreed on sort of a canonical framework to define what it means for an algorithm to be private. And this framework is known as differential privacy. It comes with a very strong intuition, which is the following. If you have an adversary that is observing the outputs of your algorithm, right? So you can see outputs 1 to n here. They shouldn't be able to tell whether the randomized algorithm was operating on this first data set here or this second data set. So let me now explain what's the difference between these two data sets. The first data set contains all these data records here, including the one in green, which corresponds to this particular individual. Instead, the second data set is identical, but it does not contain the record in green that corresponded to that particular individual. What this means is that if the adversary is looking at this algorithm, they can't tell whether it's operating on this data set or this second data set. So it has no idea whether this individual contributed their data to the data set or not. Okay? And that's how they get privacy, because the individual has some sort of plausible deniability that they didn't contribute their data anyway, so we're not learning anything about them. Okay? Of course, if we didn't learn anything about them, we wouldn't be able to learn anything at all from any of the data points. And so what we have to do is tolerate a small amount of information leaking for each of these data points, but we're going to bound how much is leaking from each of these data points. And this is what is here at the bottom, which is the guarantee we're trying to prove. We're saying the probability that our algorithm M makes a certain output S on a data set D, which would be here the first data set, has to be very close from the probability that the same algorithm M make the same output S on a second data set D prime, which is the second data set. And so what this means is if these two probabilities are close, the adversary can't really improve their guess significantly of the different features that are contained in the individual's data point. Okay, and so how close these probabilities are is controlled by this parameter epsilon. The smaller we can show epsilon is, the stronger the privacy guarantee is, because it's harder for the adversary to guess in which setting we are. And we have to prove that this epsilon holds for all possible D and D prime that only differ by one training record. Okay, all possible pairs. And if that is true, then we say that the algorithm is differentially private. Okay, how do we obtain differential privacy in machine learning? Well, there are a couple of approaches here. I'm going to introduce one because it allows me to give you some insights into what privacy means for machine learning, how aligned it is with generalization. But you can also read online about other approaches like differentially private stochastic gradient descent, for instance. So the idea here is to take the sensitive data here on the left and to split it in multiple partitions. Rather than train one model on this entire sensitive data set, we're actually going to partition it and then train a different model on each of these partitions, okay? And so here there's nothing that needs to happen in particular when you train the models. The only requirement is there is no overlap between the different data partitions. So if one point is here in this large data set, it will be containing only one of the partitions. And so what that means is that only one of the teachers will have learned from them. Okay, and so we have this ensemble of models, these teacher models. They all have learned about the same task, but from different data sets. Okay, and so now how do we have them predict with privacy? Well, we could say send an input to this ensemble of models and take the argmax. What is the most commonly predicted label? That gives us some privacy in the sense that we can see that if I'm in this data set, I'm only going to be in one of these partitions. Okay, and so I only influence one of the teacher predictions. And so what this means is when I take an argmax, I'm having a relatively small influence on essentially the aggregated prediction. The problem is that if half of the teachers agree on one label, half of the teachers agree on the other label, then we can get situations where me adding my data into the data set can mean that I'm going to flip the prediction of one of the teachers, and this will turn into a situation where now we're changing the label that received the most number of votes, because it's not just one more, it's just added one more vote into one of the classes and removed one vote from another class. And so now we've flipped the order of the labels that received the most number of votes. Okay, and so to prevent this, this is where we have to introduce randomization. This is where instead of taking an argmax on the histogram of votes directly, we're going to first randomize the votes by introducing a little bit of Gaussian noise on the vote counts. And then we'll take an argmax. And then when the adversary, for instance, would change one data point, they wouldn't be able to know why the aggregated prediction changed. Is it because the noise that was sampled changed, or is it because the data point actually had an effect on the prediction? And this is how we get essentially a setup where each prediction that the aggregated teachers makes is a prediction that comes with differential privacy guarantees. Okay, and so this is here on the left. And so now I'm going to answer the question. Thank you for the question. What does the student model learn? What is the query? I'm going to tell you right now. And so the idea here is that every time that the aggregated teachers are being asked to make a prediction, there's a small amount of private information that is leaking. Because if you remember, I told you in this definition that we can't ensure that the probabilities are exactly equal, otherwise we wouldn't be able to learn anything. So we're going to have a small epsilon, but a non-zero epsilon that tolerates a bit of information leaking. And so every time that we respond to a query, which would be, for instance, a test input, then it's possible that the adversary learns a small amount of information about the training set. So this is why we need to introduce the student model. And what we're going to do is we're going to transfer the knowledge that the ensemble of teachers have acquired into the student model with privacy. And how this works is that we assume the student model has access to public data that we do not need to protect the privacy of, but that data is unlabeled. Okay, and so to learn, basically to train the student model, we need to get some labels for this public data. And that's where we're going to use the teacher models. We're going to ask them to predict with their noisy aggregation labels for the public data. And these labels are produced, again, with differential privacy, but we're going to use them to train the student model. Okay, and so why does this solve the problem that I described before? Because once the student model is trained, we don't have to query the teachers anymore. So the privacy cost is bounded and fixed at the end of the training procedure for the student. But then the student model is a normal machine learning model. We can use it to respond to as many test inputs as we'd like. So these are the queries here on the right, where people will send requests to classify an input, and we can use the student. We can answer as many queries as we like. Okay, and so what happened is that we took what is in the ensemble of teachers that was learned, that is sensitive, and we transferred that knowledge into the student model in a way that is privacy preserving. And then the cool thing about this setup is that we can also leverage advances like semi-supervised learning to decrease the amount of queries that we have to, the amount of public data that we have to ask the teachers to label. And so that can further improve the trade-off between the accuracy of the student and the privacy that we consume by training the student. Okay, and there's this very nice intuition here between differential privacy and generalization, in the sense that once more of the teachers agree on the prediction that they are making, we have both benefits for privacy and generalization. Okay, why? Because if more teachers agree on the prediction, then it's more likely that this prediction is correct because it was made multiple times on by models that were trained on independently sampled training set. So in basically data sets that have no overlap. Okay. And then the reason why it's more likely that this model is this prediction is more private is that if more of the teachers agree on the prediction that they're making, then what this means is we can add more noise to their votes before we start changing the result of the aggregation. And so because we introduce more randomization, then what the analysis shows us is that we can prove that the indistinguishability between these two settings is much stronger. So we get stronger privacy guarantees, which makes sense because if more teachers agree, it's harder for one teacher to flip the outcome that is predicted. And so we get this notion of privacy. So let me just take one question. Yes, so when we introduce the randomness, so I just talked about how randomness improves privacy, does that decrease the accuracy of the teacher and then the student? So yes and no. So it does, there's sort of a trade-off here. So initially, when you introduce noise, if there is sufficient consensus, and this is kind of what I was explaining, then introducing noise is not going to impact the aggregated outcome, because the amount of noise that we introduce is not sufficient to change the histogram of votes sufficiently significantly, such that the label that receives the most number of votes has changed. That said, at some point, as we continue increasing the amount of noise we introduce, we are going to get to a point where now we are starting to change the predictions that we're making when we take the aggregated argmax, okay? And so this is when we would see a drop in the performance eventually. And so there's this trade-off where we have to basically understand how much privacy we can get while not minimizing the performance of our model too much, okay? But then once we have, once we have fixed this mechanism, the student's accuracy is a function of both the public data that's available and how accurate these labels are. But it is sometimes possible to recover some of the performance if we have good public data, okay? But that's a very good point. And actually, that's something that I wanted to comment a little bit more on, because what we realized with CARTE, which is very cool, it happens very rarely in security research, is that we have this opportunity to increase simultaneously how private the prediction is and how accurate it is. And how do we do that? Simply by enforcing that there is sufficient consensus in the teacher's predictions. So what I just explained to you is that when there is high consensus, the prediction is more likely to be correct and can be made more private because we can introduce more noise. And so what we found in this follow-up work is that we can actually threshold for a minimum amount of consensus before we decide to even proceed with making a prediction on the input. And so what we end up doing is we spend part of our privacy budget deciding which queries we want to predict on, and then the rest of the privacy budget actually answering and giving a prediction for these queries. And we found that by introducing this consensus check, we were able to improve simultaneously how private our predictions are and how accurate they are, which is really nice and shows that differential privacy essentially is a worst case property that implies a form of generalization, but the other way around doesn't work. Because generalization is average case, it doesn't imply privacy. Okay, and this is where I want to contrast this part of the talk with what happened in robustness before, when I was talking about adversarial examples. In adversarial examples, we had these kinds of arms races where I showed you how we can introduce, for instance, randomization as a defense. But then as we develop more attacks, we understand that the benefits that we were observing in terms of robustness are maybe not as sustained as we thought. And this is something that happens regularly. Before that, we had shown how, for instance, gradient masking appears like it defends models, but in the end can be evaded using black box attacks based on transferability. Here, as we were introducing randomization in the models to provide privacy using this noisy argmax mechanism, we actually see that we have sustained robustness to privacy attacks, okay? And so I'm going to show you an example here in the context of membership inference, which is a form of privacy attack where we were giving a data point and we'd like to know whether that data point was contained in the training set or not. Okay, so we are able to interact with the model. And one signal for whether a point was a member of the training set or not is how confident the model is in its predictions on this point. And this is actually something that people have observed, and a lot of attacks on models that were performing membership inference actually did some form of confidence thresholding. And so there were defenses that were proposed, you can see where this is going, where people said, well, let's not reveal the model's confidence, or let's obfuscate it in some way. And then we'll see that if we mask the confidence, then the model will become more robust, quote unquote, to these membership inference attacks, because we are no longer giving the signal that they rely on. And so what we did in this paper on the right is that we came up with a membership inference attack that only requires label access to the model. And so this is what we see here. We were able not only to come up with such an attack, but an attack that performed equally well to the confidence-based attack. So the confidence attacks are in the blue line, and our attack that only requires labels is the orange line. And so you can see they're overlapping, basically the same performance. What this means is that as an adversary, we have now learned that we do not need access to the confidence. So therefore, all defenses that were relying on masking the confidence score are now broken by design, because we don't need the confidence score in the first place to decide whether or not a point is a member. And so this is very similar to what happened in robustness research, where we have these attacks and defenses that are always alternating. Here we can see the same thing if we try to come up with these ad hoc defenses in privacy. However, if we use what I just described here with randomization that leads to differential privacy guarantees, then we actually notice that this is where we get robustness to these new attacks that we did not even know of when we designed these privacy-preserving algorithms that introduce randomization to get differential privacy. And in fact, they achieve the best trade-off between utility and robustness to these membership inference attacks. And so this is where we can see how in the privacy literature, people have managed to leverage randomization extremely effectively to get solid guarantees that are rigorous, that sustain themselves despite progress in how the attack is conducted. And the reason is that the definition of differential privacy does not make any assumption about what the adversary knows or is capable of doing. And so this means that now the attacks that are sort of becoming more sophisticated are not actually able to evade these randomized based mechanisms like the one that I just described here with the noisy argmax in the pate approach here, which is what I was talking about. Okay. And so this is very important, because if we don't use differential privacy to protect the privacy of training data in machine learning, then we can see that we can come up with lots and lots of attacks against the training points. And so here is another example, because I know there's a lot of discussion of how federated learning could be used to protect private training data. Well, in the vanilla form of federated learning, when there is no form of randomization, there is no guarantee of differential privacy, there is actually no guarantee of privacy at all. And in fact, if the user is unable to trust the central server, federated learning does not provide them any guarantees whatsoever in terms of the privacy of their training data. So let me explain what happens here. In federated learning, the idea is to say, well, rather than having different clients send their data points to a server that would then train a model centrally, we're going to send gradients back to the server, and then the server will use these gradients to compute the model. Okay, and so the idea is to say, well, if I send gradients, I'm not sending my data, so I have this form of data minimization, or you can think of it as a form of privacy. But really, what we showed in this work, and this is work led by Francisca here, that there is actually no such benefit to the end user, because if the central server is untrusted, all they have to do is look at the gradients, and the gradients contain the data points themselves. So here, what I'm showing you is the original training points, and here these are the extracted data points that Francisca was able to obtain simply by looking at the gradients. I tried to convince her to call this paper "All You Need Is a Matplotlib," because really all you have to do is take the gradients of the different clients and pass them on to Matplotlib, and this is what you get. Okay, so why is that the case? Well, if you look at what the gradients contain, they're actually computing gradients of the loss with respect to the weights and the biases. And so if you have, for instance, a linear fully connected layer that is computing essentially a weighted sum of the different inputs to which you apply an activation function like ReLU, well, if the input to that function is positive, we are actually just looking at Wx plus b being computed by an individual neuron, okay? And so what does that mean? Well, if we look at the gradient of the loss with respect to the weight, it's actually equal to the gradient of the loss with respect to the output of that neuron times the gradient of the output with respect to the weight. And this is exactly equal to the gradient of the loss with respect to the bias times the input. Okay, what is the problem here? When the client participates in federated learning, they are going to send back two things to the server, this gradient here, L with respect to B, and L with respect to W. This is what I showed here, okay? And so you can tell that how do they get X if you're the central server? You just look at this gradient, you rescale by this factor, and you get exactly X, which is what I was showing here, okay? And so we can do the same thing when there are multiple data points in a mini batch. The reason is that despite the fact that we are now summing and averaging this computation over multiple points, we can actually recover some of the data points in the mini batch because not all points activate the same neurons. And so this means that some neurons remain activated by a single point in the mini batch, and this is what you can see here, whereas some of the other neurons are activated by multiple points, so they don't allow us to reconstruct anything. Anyways, so what I've shown here is that in federated learning, if we don't have any form of randomization, federated learning in its pure form, it doesn't provide any privacy protection against passive leakage that occurs when the server is malicious, okay? What we would need to do here is to use both secure aggregation to ensure that the different clients are sending gradients that are aggregated before the central server would have access to it. But more importantly, we need to introduce differential privacy guarantees into this whole setup. And so here, what we show is that as we introduce more noise, thanks to a differentially private optimizer, you could use something like PATE that I talked about before, a differentially private stochastic gradient descent, where you would introduce noise to the gradients and also clip these gradients. And you can see that as you introduce more and more noise, then the ability to recover private information decreases. And so this is, again, a good example of how randomization is required in privacy to obtain significant guarantees. And that here we have figured out a way to obtain this privacy guarantee using randomization effectively. The key problem here, though, is, and this is something we're still working on, is that it's very hard to know as a user how much noise I should add to my gradients in order to get guarantees that are basically sustained when I cannot trust any other participant in the protocol, and of course, when I cannot trust the central server. And so this really shows how key it is here to select the right amount of noise that is being inserted to get the privacy guarantee. And so this remains sort of like an open sort of practical question, how individual users should calibrate the amount of noise. And again, it shows how fundamental it is to understand the role of randomization to the privacy guarantee that we're getting. Okay, and so I hope that this basically showed you how in privacy we know how to use randomization. We're still working on the calibration of the randomization, which is fundamental to getting practical guarantees that are meaningful to the end users. And whereas in robustness, we don't really understand very well how to use randomization, except in some of the experiments I mentioned in passing that we've conducted on in the audio domain. Before I take any remaining questions, as Sumaya mentioned before, I'm organizing a new conference called SATML, Secure and Trustworthy Machine Learning, sponsored by IEEE. I'm very excited it's happening next week. So if you want to take a last-minute trip to SATML, feel free to register. But more importantly, we are going to announce soon the next iteration of the conference for 2024. And so you'll see there will be a call for papers, as well as a call to participate in the reviewing process. So I very much look forward to your participation in this new important conference. with this, I will thank both our sponsors for generously funding our work, as well as all my postdocs and students who have been participating in this research and who are really driving the projects that I talked about today. So please do not hesitate to reach out to them if you have any questions. And I will be happy to also answer a few more questions. I see we have 5 minutes left. Thank you for your attention.
So I think there is one question, Nicolas.
Yeah, I'm looking through it. Okay, yeah. So those are very good points.
Actually, can you read out the questions too? I don't think everyone. Yeah.
The question is asking if there are other components in basically the architecture of the model, such as batch normalization, dropout. How does this affect the extraction? So again, if we have things like batch normalization and dropout, the signal is still there. So you'll see if you pull up the paper. So I would recommend basically going on Francisca's website if you search her name online, and then you can look at this paper. She also has a more recent paper where she looked at more of these modifications. And essentially, batch normalization, dropout, they don't make the reconstruction impossible. They make it slightly more complicated, okay? And the reason, as you can guess, is that you're now dropping some of the information, so you have to repeat the attack more, or you have to target more neurons before you're able to reconstruct as many data points, okay? But fundamentally, it doesn't prevent the leakage that is happening here. And then to answer the second part of your question, which is a great question, whether we still need gradient clipping and noise addition, yes, we still need gradient clipping and noise addition. There's no way to evade the need for gradient clipping and noise addition. Why? Because if we want to prove differential privacy, the gradient clipping is required to be able to control the sensitivity of the learning algorithm to the training points. And so the sensitivity means if I change my training point, how much is the output of the algorithm going to change? If we don't have gradient clipping, we will not be able to know what the sensitivity is. For the noise addition, again, the fundamental role of randomization, we cannot have privacy without randomization. It's just not possible to obtain differential privacy without randomization. And so here we also have to add noise to the gradients. And again, you can see why here, where if you have no noise, you're essentially computing gradients that contain the features of the input as part of the sum of the components of the gradient. And this is the same thing that if you go back to Pate here, if you take the argmax, the aggregation of the teacher votes with no randomization, it will provide some form of intuitive privacy in most cases, but not in the worst case cases. And this is where privacy is the most important when you have worst case inputs, such as what I described, where you have half the votes in one class, half the votes in another class, then changing one point can flip which class wins this argmax. And that's where you need randomization. And you would not be able to prove differential privacy if there is no randomization. The randomization basically provides this indistinguishability, this plausible deniability for some of the points that are the most exposed in terms of privacy leakage. And so the same thing happens here with federated learning. You need to use differentially private stochastic gradient descent if you want to have any form of privacy guarantee that actually protects against private information contained in these different client data sets from reaching the central server and the model itself. A general question in terms of privacy and data fed into machine learning models besides differential privacy, are there any other formulations of privacy measures? Absolutely. Differential privacy, I'm sort of showing how important it is here with randomization. It's not the only definition of privacy, of course. There are other guarantees that people have been working on. For instance, recently, there's a lot of legal developments where people have proposed things like the right to be forgotten or other variants of allowing people to delete their data sets. So for instance, here you could imagine that some of these clients might decide later on that they no longer want to contribute their data points to your model. What if you've already trained the model? What do you do with that model? Well, you could say, if I trained it with differential privacy, the leakage is bounded, so that's one thing. But some clients might still tell you, I want my data to be completely removed from your model. And so you now face this problem that we looked at, which is called machine unlearning, where you're now taking a deployed model and you want to remove some of its training points. So you have to update the model and remove the influence of these training points. So this is, for instance, another form of privacy that is different from differential privacy in many ways. If you are interested in this, I recommend that you look up Envith Tudi's website, envith.com, where he basically has a couple of papers on the problem of machine unlearning, and will show you what kind of approaches will allow you to make progress towards being able to claim that you have removed training data from models that were previously deployed. So that's an example of another privacy measure. There's also, just very briefly, a whole other set of concepts known as privacy that are more related to sort of cryptographic aspects, where the idea is to say that you want to, for instance, be able to take in as inputs to your machine learning model encrypted inputs and be able to make predictions on encrypted inputs without having to decrypt the inputs to make the prediction. And so that provides a different form of privacy in the sense that it controls who is able to read the input. So only authorized parties are now able to read the input in plain text. And so this can be very useful, especially in decentralized settings. If you look at Adam Gigic's website, you'll see that he has work on something called CAPC, where he's using this these concepts from cryptography to allow parties that have models, basically, as you would have in Pate here, you have multiple teachers, but now these teachers are not all trained by the same party. They're trained by different persons, different hospitals, different companies, but these companies still want to be able to make predictions together. And so using this form of cryptography, you're able to allow them to predict together on inputs that are encrypted. So you have this nice different guarantee that now nobody is able to read what they're predicting on. And so that provides you with a different form of privacy, something we call confidentiality most of the time, but you might also think of it as a form of privacy. So I hope that gives you a couple of examples. And I think we are just out of time. So I'm not sure if more people have questions. I guess you can always shoot an email.
Yeah, I don't see any more questions either. So in the interest of time, I'd like to thank you very much for this very interesting seminar. I personally learned a lot. I'm sure everybody else did that the same. I also like to thank our colleagues at the University of Seoul for co-hosting this seminar series, and I invite everyone to attend the rest of the seminars we have in the upcoming weeks. Thank you, everyone.
Yeah, thank you so much for the great question.